Good morning, everyone. We're the Accident Aviation Analysis Group, and this is our project. And we basically analyze NTSB aviation analysis data from the year 2008 all the way to the year 2024 to predict fatal versus non-fatal crashes after cleaning and merging four NTSB datasets. So basically, we found a way. How would we send data faster to first responders during life-saving information periods? And the inspiration for this project came from me and my good friend Hunter. I used to jump out of a plane. He would fix them in the military. And that's where we realized, yo, we need to fix the situation we have currently with the planes. And we need to make sure that like first responders get better information.
We began our machine learning model journey with the K nearest neighbors model, which was our baseline classifier. Mm, We decided to use the features location, weather, lighting, and engine type to train our model to see if we could accurately predict our target, which would be non-fatal versus fatal accidents. Originally, we returned an accuracy score of 85%, which seemed promising at first, but after further investigation, we saw that there was a large oversampling of non-fatal accidents which was returning such a high accuracy score. Once we undersampled the data and had an even number of fatal versus non-fatal accidents, the model predicted an accuracy score of 58%, which showed that the Canaan model was not reliable for rare fatal crashes and thus had us pivot to the random forest and then the XG boost.
For our second model, we transitioned from KNN to random forest after recognizing that class imbalance was severely limiting prediction accuracy for fatal crashes. Fatal events made up only about 17% of our data, so any model that defaults to the majority class ends up performing well on paper, but poorly when it actually matters. Our first attempt at balancing the dataset used global undersampling, where we removed thousands of non-fatal crashes to match the number of fatal ones. While that did level the classes, it also threw away a massive amount of valuable data, which weakened the model's ability to learn real-world variation. We were losing information from thousands of legitimate accident records, which is not ideal for life-saving predictions. To fix this, we adopted a per-tree balancing system within the random forest. Instead of shrinking the dataset, we allowed each tree to learn from a balanced mix of fatal and non-fatal crashes. This kept 100% of the original data while still improving representation of rare fatal cases. After tenfold cross-validation, our final random forest achieved an accuracy of 77.9% with a balanced accuracy of 77%. Most importantly, recall for the fatal class improved to 60%, meaning the model correctly identified over 60% of fatal crashes, which is a major leap from Model 1. However, the model still struggled with low precision and continued to misclassify many fatal crashes as non-fatal, which pushes us to search for a more advanced method capable of learning from rare but critical events. This led directly into the development of Model 3.
All right, so for Model 3, we use an XGBoost model, which is an algorithm that handles messy data really well. And it was used to create our emergency data drop, which is a system that takes our project and applies it to potentially save lives. And the whole idea behind it is super simple, but yet also super powerful. If trauma centers have quicker access to more data, then the more lives that could potentially be saved. And I'm about to show you what the system can display. Switch over here. Let's type in Arizona since that's where we're at right now. Run that and it'll pinpoint on the map of a crash site as well as information that the EDD supplies. So let's zoom in, click on that. And as you can see, this is the information that this system can provide. So it'll tell you if a crash is likely survivable or not. And at 0.48, it's survivable, as well as the nearest hospital, which is Banner Baywood, and it displays it as a level 3 trauma center, and it's about 128 miles from the crash. And the best time to care for that is 84.4 minutes, which is probably by air.
While our first three models focused on classifying whether a crash was fatal or non-fatal, Model 4 shifted the objective entirely. Instead of predicting if a fatality would occur, we wanted to predict how many fatalities might result once a fatal crash happens. This allowed us to move from a yes or no outcome into a more practical severity estimation that could help emergency teams prepare the right level of medical response. To build this model, we filtered our dataset to only include accidents where at least one fatality occurred. That way, the model learned patterns specifically associated with fatal injury outcome or counts, rather than having to distinguish between fatal and non-fatal events. We then used a random forest regression approach because of its ability to capture non-linear relationships without requiring heavy pre-processing or strict data assumptions. We trained the model using an 80-20 test split and evaluated performance using root mean squared error and mean absolute error to measure how close our predictions were to the true fatality numbers. The final model achieved an RMSE of 0.736 and an MAE of 0.414, meaning on average our predictions were within less than half of 1% of the real fatality count. Variable importance reached that exposure and situational factors like total occupants on board, number of seats, time of day, plane hours, and temperature were the strongest predictors of fatality magnitude. This makes intuitive sense just because more people on board increases the possible loss of life, while environmental and timing conditions shape survivability and response constraints. Overall, Model 4 expands our project's capabilities by going beyond binary outcomes and offers a more detailed look at fatality severity, giving emergency planners a deeper level of information when assessing potential medical resource needed in aviation disaster.
To conclude, basically, a real-time system that predicted injury severity and injury likelihood sends it to hospital and first responders, helping reduce any delays between uh, response and preparedness.